In this new chapter, we discuss an important adaptation of our thermodynamic model when we deal with the different fluids, like mixture of gases or gas plus vapors. We remember that a mixture is a combination of two or more substances in gaseous form to become an homogeneous new substance, still gaseous. The mixture can change for type or substance, but also for composition, that is the percentage in mass of each substance. Since of the variety of the mixtures that we can achieve, it is almost impossible to manage them with applications we have seen up to now. They are thought for specific substances only. Exception is the mixture air and water vapor at ambient pressure. This mixture is very important to study the climatization processes. This special case we can treat with a psychrometric chart and the corresponding tools. We will see this in the next lecture. Let's consider a recipient where two ideal gases are mixed. The volume is capital V, the pressure P. The pressure of the recipient is the sum of the partial pressures of each gas. P equals P1 plus P2. The temperature is the same and the mass M equals M1 plus M2. The state equation says P1V equals M1 R1T, P2V equals M2 R2T, where R1 is R0 over PM1, R2 is R0 over PM2. R0 is the universal constant of the gases, and PMI the molecular weight of the gas I in kilogram per kilomole. If we sum the two state equations, we get P1 plus P2 into capital V equals M1 R1 plus M2 R2 into temperature. Therefore, P into V equals MRT, where MR is for definition the sum of M1 R1 and M2 R2, and we can find the formula 40 to define the constant of the mixture in case of two substances. Another way to find the gas constant is the ratio between R0 and the molecular weight of the mixture, where the molecular weight is given by this formula. Ni is the number of moles of the gas I, or we can write in this form x1 into PM1 plus x2 into PM2, where xi is the molar fraction of the gas I. If we generalize for a mixture of n gases, we find the formula 43, where Ri is R0 over PMI. In this lecture, we use for the mass m in lowercase. Another way to find the gas constant is, as we have said, R0 divided PM, where PM is the sum of xi into PMI, being xi the molar fraction of the gas I. The mixture behaves as a single gas having R calculated as above. What about Cp and Cv? Cp we can calculate as a pounded average between the Cpi of each gas, being the pound the mass fraction, the same as we have seen per R. And what about Cv? Cv is, for definition, Cp minus R. This relationship is valid for both ideal and perfect gases. We remember that for a perfect gas, Cp and Cv are function of the temperature, therefore they are not constant. For a real gas, we cannot use the simple state equation Pv equals RT instead, therefore above considerations are not applicable. What about if the mixture composition is known in volume? In such a case, we need a different approach. Let's start with an example, the gas air. And we know that air is a mixture of different gases. We consider for the time only two of them, oxygen and nitrogen. Oxygen is present in a percentage of 21% in volume and nitrogen 79% in volume. The pressure is the same. We can write the equations of the ideal gases in such a way. Pressure into V1 equals M1 R1 T. Pressure into V2 equals M2 R2. Therefore, the ratio between V2 and V1 is the ratio between M2 and M1, PM1 and PM2, because R0 cancels out. If we solve for the ratio of the masses M2 over M1, we find this value, 3.29. And if we consider that the sum of the masses is 1 for definition of the mass fraction, knowing the sum and the ratio, we can get the single mass fraction. M1 is 0.23, M2 is 0.77. And with the formula 40, we find for the gas constant of the mixture the value 288.4 joule per kilogram per Kelvin. The real value is slightly different. It is 287.06, taking into consideration some more gases, and in such a case the molecular weight is 28.96 kg per kilomole. For a volumetric known mixture of n gases, we can use this formula to find the mass fraction, where the sum of the single masses is the total mass. The gas constant can be found with the formula 43 once the mass fractions are known. We notice that we don't need to know the total mass because it can be assumed unitary for the purpose of the calculation. We make an example with a mixture of three ideal gases: nitrogen, hydrogen, and CO2. The percentage in volume, the molecular weight, and the Cp are given. Let's calculate R. The easiest way is to use the formula 44, remembering that Xi are same as volume fraction. Therefore, Pm is sum of Xi into Pmi, and we find 22.09 kg per kilomole. R is R0 over Pm, 376.6 joule per kilogram per Kelvin. To calculate Cp of the mixture, we need to transform the volume fraction into mass fraction using the formula 46, where we can put the sum of the masses equal to 1. We find for M1 the value 0.41, for the mass 2 0.04, and for the mass 3 0.56. The heat capacity at constant pressure, assumed independent from the temperature, this is valid only for the ideal gases, can be found with the formula 45, 1418 joule per kilogram per Kelvin. For completion, we calculate also Cv and K. Cv is Cp minus R, 1041 joule per kilogram per Kelvin, and K is the ratio between Cp and Cv, 1.361, dimensionless. With the above data, we can calculate any thermodynamic cycle of the gas. For example, the cycle made by the transformations A isochoric 1,2, B isentropic 2,3, and C isobaric 3,1. Given are the variables in red square and the others are calculated. We have used here the tool Thermonator, but we can calculate also with the formulas we have seen for the ideal gases. We want to find now the work and the efficiency of the cycle. We assume the unitary mass. Q12 is CV into T2 minus T1, and we find 390.6 kJ. The thermodynamic work is 0 because the transformation is isochoric. Transformation B, Q23 is 0 because adiabatic. Thermodynamic work 23 is R divided 1 minus K into T3 minus T2, we find 136.3 kJ. Transformation C, Q31 is Cp into T1 minus T3, negative 346.2 kJ. Thermodynamic work 31 is P3 into V1 minus V3, we find negative 91.9 kJ. The work of the cycle is the sum of the works of all the transformations. We land to 44.4 kJ, and the efficiency is, for definition, the work divided by the given heat Q12, 11.4%. Thank you for your attendance. In the next video we will see the mixture between a gas and a vapor. See you again. Bye bye.